Hi, my name is Juliet Shelton, and this is my Lab 5 on Faraday's Law. So first, in this lab, we are looking at a real-life example of induced currents in magnetic fields. We are measuring the force of the external field from a bar magnet and the induced current from inside of the tube of the aluminum foil. And then we are trying to see how the speed of the falling bar magnet inside of the tube is affected by the induced current, the magnetic field, and the magnetic flux. So some fundamental principles we are using in this lab are magnetic flux and Faraday's law. Magnetic flux is measuring the total magnetic field that passes through a given area. And then Faraday's law is when the magnetic flux in a circuit changes, the electromotive force is induced in the circuit and is proportional to the rate of the change of the flux. So in this lab, first I used my smartphone to determine which end of the magnet is north. Then I held the aluminum foil tube vertically and recorded a video, dropping the magnet through the tube. I recorded how long the magnet was inside of the tube and then repeated this step 5 times. So some observations that I found was first, the magnet slowed down to a constant velocity while inside of the tube. And then without the tube, the speed of the magnet would not have changed as it fell. Also, the magnet had an increasing magnetic field regardless of the orientation. And then the upper current on the bar magnet created a magnetic pull upwards, causing the magnet to slow down. So these are the results from my trials, and then also some initial measurements. So the length of my tube was 0.305 meters, the tube inner radius was 0.024 meters, the tube width was 0.0061 meters, and then the tube radius, which is the width plus the inner radius, is 0.0301 meters. And then averaging the time that it took from all of my trials, I got the average time for the magnet to fall through the tube was 1.278 seconds. So here's my code. First, I inputted the geometry of the tube, and I included the length, width, and radius measurements of the aluminum foil. Then I worked on the magnetic field function for the bar magnet. I took this from my Lab 3 code, and then I worked on the magnetic flux function. After that, I used my code to calculate the current in the ring, the magnetic field at each ring, the net force on the magnet's velocity and position, and then my final print functions. So then here are my computational model results. On the left, you can see the velocity versus time graph, and on the right, you can see the tube and the magnet. So then interpreting my code, the intensity of the color on the tube indicated the magnitude of the current flowing through each ring. And then the colors red and blue indicated the direction that the current was flowing. So red indicated that the current was flowing clockwise, and blue indicated that the current was flowing counterclockwise. So then we were asked, what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? So from Lenz's law, we know that a current will be induced to flow in the tube to create a field that will cancel the magnet's increasing magnetic field. So if the resistivity of the conductor was reduced as close as possible to zero, the tube would not be able to create a field to oppose the magnet's increasing magnetic field, and then the magnet would fall as if there were no conductor at all. And then we were asked, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? So we would make it would make our computational model more accurate if we broke the tube up into more rings.